Hello guys. So now what we'll do is the following. We will understand more about correlation. Okay. So what is correlation? Where did it finally come out? I told that R is actually defined. The correlation is defined as R square rather is SXY by SSX. SS are actually by SSY this right. So just ignore my tongue twister stuff. Okay, whatever. So R is equal to SXY by root over the variance, the standard deviation X and standard deviation of Y, right? So we understand where this suddenly comes up from. So if you remember that from normal equations, we got the following results. Let's try to see them, go back. We got that yi this will need this too, and we got the beta 1 hat. Okay, so let's try to understand that in much more details. So we have got these three equations. Which three equations? First one is y1 hat is equal to beta naught hat plus beta 1 hat into xi. We have also got y bar equal to beta naught hat plus beta 1 hat into x bar, and we have got that beta 1 hat is equal to sxx by sxy by sxx. Okay, so now let's see what we can explore from here. So if you try to understand, observe that we have a data like this. Okay, what we'll do, this is a mean x bar comma y bar, say this is a yi. So what we'll do, we'll standardize yi. Okay, each of the yi hat. So let's try to understand yi hat minus y bar. Okay, so let's try to understand that. If we do yi hat minus y bar, we get what? We get beta naught gets cancelled, beta naught hat, we get beta 1 hat into xi minus x bar. So let's write down beta 1 hat. We write down beta 1 hat is sxx by sxy by sxx into xi minus x bar. Okay, what we'll do is standardize x now. Standardize x, what we need? We need to divide with the standard deviation syy, and we need to divide by sxx. For that, what we need to multiply? We need to multiply 1 by syy and we need to multiply sxx. Okay, so what do we get? Let's see. So these are the extra terms over here. Let's combine these two and we get the following beautiful stuff. yi hat minus y bar by root over syy is equal to sxi minus x bar by root over the standardized x and the standardized y into, also it's sxy by root over sxx into root over syy. Beautiful, no? So this is actually what we call R. This is the correlation coefficient. So why is it naturally comes? Sort of it means that this correlation coefficient, this means if you can read the equation, it means this. So if standardized y, let's call it standardized yi, syi, okay? And let's call sxi is a standardized x. So observe that syi is actually r times sxi. This sort of the correlation, so it sort of gives us an idea how much x is actually dependent, how much x varies to get with how much varying in x with respect to the standard deviation of the x data, y will vary. Okay, and this is the basic idea. Okay, what we'll get. But before that, we will get to understanding what is the meaning of regression towards the mean. But before that, let's do the proof of correlation, like the inequality of correlation. Okay. Perfect. So let's try to do the inequality of correlation now. What is the inequality? So we have got what? We have got R equal to sxx by root over sxy by root over sxx by root over ssy. I'm just spelling it wrong every single time. I don't know why. So Anyways, so now what we'll do, it's something called Cauchy inequality, Cauchy-Schwarz inequality. I may be very wrong with the spelling of scores. I do it every time wrong. Let's try to understand what is the Cauchy-Schwarz inequality. It has a simple following thing. Summation ei square from 1 to n into summation bi square from 1 to n is greater than or equal to summation ai and bi, okay? Where ai and bi are what? Are real numbers. And the equality holds if and only if, remember the statement it's required here, ai by bi is equal to constant for all I. Okay, this is a Cauchy inequality, and this is a very beautiful inequality. I love this. It can be interpreted in terms of vectors. Okay, that's why this R has a relation with the vectors. Okay, so how it's interpreted, Cauchy inequality in the following manner, that if V is a vector A is equal to A1 dot AN, and B is equal to B1 dot BN. The dot product of this two is this, and the length of this modulus of A square and this modulus of B square. Dot product of A vector dot B vector is actually, so the idea is that dot product of this by modulus of A by modulus of B is actually cos theta. Okay. Actually, it's I think it's square. Yes, I have done it wrong. So therefore, the idea is that if it's cos theta of the angle, you can easily prove it by geometry. If it's by cos theta of the angle, then A vector dot B vector by modulus of A modulus of B is actually less than or equal to 1 and greater than or equal to minus 1. And it's, if you take it square, A dot B whole square by modulus of A square modulus of B square is less than or equal to 1. And it's actually, if you just expand it, this is the dot product A dot B, and this is the modulus of A square modulus of B square. This inequality comes up. So this is the proof of Cauchy-Schwarz inequality in terms of vector algebra. We will see that how it's related here. We'll prove, as I already told you. Let's try to understand this. R is equal to Sxx by S over Xyy and over Sy. So it's sort of Sx is what? It's summation of xi minus x bar 1 from 1 to n whole square. Okay, so it's sort of xi minus x, this thing, right? Sort of it's actually the product of the x quantities, the modulus of the x quantities, okay? And Syy is actually summation of 1 to n yi minus y bar. Actually standardized, not standardized, but like mean with mean changes, mean corresponding with respect to the mean, okay? So, and what is xyy? Sxy, it's summation of 1 to n xi minus x bar times yi minus y bar. So it's actually a dot product of x dot y, right? It's a dot product. So as we understood from diagram, that x dot y by the Cauchy-Schwarz inequality, actually what we will get? We'll get that summation of xi minus x bar times yi minus y bar is less than or equal to summation of xi minus x bar whole square, it's actually whole square over here, times summation of yi minus that handwriting y bar whole square. This is a Cauchy-Schwarz inequality. We get from here that what is we get? It's Sxy whole square by Sxx by Ssy is less than or equal to 1. That gives that r square is greater than less than or equal to 1. It also gives that modulus of r is less than or equal to 1. It also gives that r is less than or equal to 1 and greater than or equal to minus 1. That gives the proof. And also you can get the understanding that this is sort of the modulus of y whole square, the modulus of x whole square, and modulus, this is x dot y, x vector dot y vector whole square. And when it is equal, when the r is equal, actually the r is equal, it's equal to, so r is equal to 1, r square is equal to 1, if and only this equality holds. That means xi minus x bar by yi minus y bar is equal to some lambda. That means yi is actually some linear function of alpha plus gamma of x. Yi and xi. You can understand from here, right? For all I. So this is the idea that it's equal to 1 if and only if r square equal to 1 if and only if the corresponding yi and xi are linear. And this is the beauty of it, okay? And geometrically it means that what it means, they're equal when the two vectors are equal. When the two vectors, the dot product is equal to 1. It's only happening if a vector and y vector are aligned with each other. That means cos theta equal to 1. Cos theta equal to 1 if and only the theta is equal to 0. Right? That means they are parallel to each other. They are actually aligned with each other. So essentially, the vectors are multiple of one another. Okay? That's the basic idea. So this is the beauty of the geometrical aspect of correlation. Okay. So that's what we get from here, Sx and y and Sxx, how it is related to each other, okay? But the geometrical part, this makes much more sense, I guess, okay? So now, understand your regression towards the mean. So what we got from this previous video, guys, we got that, if you observe it very carefully, we got this, right? This last one. So what we get, let me write it out here, y1 minus y bar by root over syy is equal to r times xi minus x bar by root over sxx. What does it mean? It means that, now try to understand it. Suppose this is equal to 1. That means this is equal to r, right? And r square is less than equal to 1. Modulus of r is actually less than equal to 1. So what does it mean? That modulus of yi minus y bar by root over xi is actually less than equal to modulus of this, right? That means the more, so even if this is large, I mean, even if this is 1, it is actually less than either. So if x changes a little bit also by 1, y changes less than equal to 1 from x. Like it means that if you take an x, if x changes by 1 standard deviation from the mean, okay, that means it's equal to 1, then y changes less than equal to 1 standard deviation from its mean. That means y is regressing towards the mean much more, okay, because of this r's. This is the idea of y is regression towards the mean. Okay, the y is regression, like y is regressing towards the mean due to this. This is the basic idea, guys. Okay, so the predicted value thus deviates from its average by fewer standard deviations than the predictor. This is the perfect language. The predicted value changes or deviates fewer standard deviations than that of the predictors. So this is a basic idea, guys. So this is all about what is regression, what is correlation, why it's told it's regression towards a mean, and what is the beauty and inequality and geometry of correlation. I'm sure this is one of the things I really loved when I learned about it. I'm sure you must have loved it too. Okay, I see you in the next video with the estimation parts of beta naught hat and beta 1 hat, and then we'll go on to one of the most important inequalities, and let's see what's coming. Stay tuned and stay blessed. See you in the next video. Bye bye.